really confused about that little homework thing. But I was really confused. On like number 3, how we had to make the full set. Like I didn't know what.
What chapter were you in?
It was in 2.1.
Oh, okay. That one I already took it. Right? That was the one that was.
Yeah, that was.
Yeah, I did not.
But like, I plugged them in. I know where. But like, then it says what is. I don't know what format we're supposed to put it in.
I just knew.
Yeah, that's what. Yeah, that's exactly what I did.
How'd you know something?
Really exactly. For what? We didn't have it. We don't do homework every day. Once a week. But like this after this class. But it was just because we missed it one day. She sets it up for 2 lectures. Homework over the 2 lectures. And the weekend. Really?
That's okay. Or just not even.
Oh, well. Don't be too worried about it. Like, don't. Even though I'm not in certain classes, I usually don't. But I'm just too busy.
I don't like
Oh, really?
everyone else. A lot of other people are fun do it. I really like some history.
It makes all the difference.
Not really.
If you like it,
Yeah.
I would have a really hard time.
One thing is like,
What? AP Chem, did not take AP Chem.
Last year, my teacher got 14 ones and 3 twos. And this year he got 4 ones, a 3 and a 5.
No.
I got a 3 and you got a 36 on this. You got a 5. It is bad also.
That's not fair. So probably has to be.
Last year, top grade in my class.
Hey there, how are ya?
Good.
Listen, I took the hardest class I ever took.
How many people are in this class?
There's 3 of us.
Astronomy with.
Has it been okay in this room? Not the best, but
It's not my favorite.
they had to. This is the smallest class this time. All the other rooms are big.
Yeah, I looked.
Oh,
We
didn't
were in
split.
the other room.
Well,
and
because Norman so only had a couple, but she.
that's what the one girl said. She said she comes here.
Biology, chemistry, physics.
That's how ours is.
They give physical science and science. That's what it is. Covered in physics. Or anything else.
Well, like I said, I'm in the water. It was the hardest class I took. You would really like our really. Well, maybe this would
I hate it.
why?
Because
I almost think all of the questions I read. I guess not. I bet she. Maybe she does. Have days.
I'm going to watch.
No,
That's
that's
watching
That's annoying because it's one of my
Yeah, I don't feel like. Yeah. Well, we literally,
I like those.
that one last thing.
That's my favorite. Milk chocolate.
what one was the first one?
Was it with the spinner on there?
It's this book, 1 and 2.
Because it
Is
says
what
what
Savannah.
Savannah.
Monday. Is what Savannah. And I had Emily give me some. Yeah, I'm just struggling to. I did actually order. That's one.
James on here.
Or not one, the other one. Which did you get?
Mm-hmm.
Wasn't sure.
I feel bad because you think I'm going to read this. Is that pretty funny? See what that looks like.
We had a new one.
Nothing.
Please don't. Just.
This one?
Yeah.
Just because. But I feel bad because it's like the only
Okay, let's check the attendance. Megan is here. Elsa. Here. Morgan. Morgan. Allison. Allison. Katie. Here. Jessie. Here. Leah. Here. Catherine. Here. Madison. Madison. Curtis.
Here.
John. All right, today we're going to continue to look at the proofs. So last time we talked about the definition of even number. So let's review that. Is Elsa here?
Yes.
Okay. Allison?
Yeah.
I'm talking about, sorry, Elsa is here. Morgan? No?
She's not here.
Allison? Morgan is not here. Allison is here. Okay. And Madison. Okay. All right. Can you all see the screen now? Slides now? Yes. Okay. All right. So that's wait, what? Oh, that's a computer. Switch. Okay. So let's look at when we started chapter 3, the proof techniques. So we're gonna first look at the proof problems in number theory. And the first one we talk about in 3.1 is the even number and odd number. Okay, so when we have an even number, not a specific even number, not like 2, 4, 6. We just know it's an even number without knowing which even number it is. We can describe it symbolically by the form of what? How do we describe it symbolically? Anyone remember? James? Yes, 2 times k. And make sure you specify here k is an integer. And this k here means integer. I mean, we could put it as 2 times integer with English word in there, but we like to use symbols. So we use k to represent an integer, so 2 times k. So, an easy question is like if someone asks you, why is 6 an even number? How would you prove it? I mean, we know it's an even number, but if I want you to prove 6 is an even number, how would you do that? By the definition. Right, so you would write it as by definition. So everything, so write in the proof, when you write down the proofs, don't take anything for granted. Anything you say, anything you write down in your proof, make sure it's either this comes from the definition or comes from a theorem or a property that we have already proved. So for example, you may say, well, 6 is even. Yeah, everyone knows that 6 is even. But if they want you to prove it, you're going to have to follow the definition of even number. So what is the definition of even number? If you can write this even number as 2 times an integer. So that's what we're going to do. So the proof, it's very easy, but you're still going to have to follow the definition to get that. So since 6 equals 2 times 3, and this 3 is the integer, and 3 is an integer, 6 is even. By definition. Well, if you want to add another one by the definition of even number. Okay, just like when you go to court and you want to defend yourself, and everything you say is, because of this law, or because of this fact, so you cannot use anything that's not from the law or not a fact. All right. That's a specific number. We also did example to prove the square of an even number is even. We can go over that example one more time here. Okay, so it says if a number is even, then its square is even. And so we are, this one is probably pretty easy, so I didn't really do any, draw any chart, but normally you could start with what's given. So what is given? We're given an even number. That's what you start with. So you start with what? You always start with what's given. What's given? Or it could be definition. So you're given an even number. And you're trying to prove. You're going to have to prove. In the end, you're going to reach your conclusion. Let's prove the conclusion. Which the square of this number is even. The square is even. So you're going to have to fill in the blank right here to how did you go from an even number to get its square is even. And so most of the problems, especially complicated ones, probably could do this, draw this chart to help you. To start, what do you start with? You always start with what's given because it says what's given is the condition here, hypothesis. If a number is even, which means we already know there is a number that's even, and then that's the conclusion that we can prove. So when under this condition that this number is even, the square of this number is even. That's unknown. Okay, so we know a number is even, but we don't know whether the square is even. Although it seems obvious, you still have to assume that you don't know that and try to prove it. So when we started, okay, because we're given an even number, so this even number, you got to describe it by its definition, 2k, k is an integer. So you want to prove the square of this number, which is 2k squared. 2k squared is even. So you want to show 2k squared is even. And how would you show 2k squared is even? So that's what we did. We worked this out, 2k squared. So here. So this is the blank that we're supposed to fill in. So 2k, we will use squared. We use the algebra formula or definition. You can do either by doing 2 squared to get a 4k squared to get k squared. Or you could do 2k times 2k. 2 copies multiply 2 copies of 2k. So when you get 4k squared, you do have to do one more step because the definition is even for even number, it says it's 2 times the integer, not 4 times the integer. So you should factor out a 2 from that 4 to get 2 times 2. And there's k squared. And you can associate this 2 with x squared, put them together, and to get the form we need. 2 times an integer. So that's exactly the definition. 2 times the integer. If you have this form, 2 times the integer, that's an even number by definition. And why is this an integer? Because when we started, 2k, that k is an integer. So when you square k, you still get an integer times by 2, you still get an integer. We do know 2k squared is it's another even integer, right? But we don't really need that piece of information. It's an even integer. As this question only asks to prove square is even. If they want to ask you, in fact, you can prove a stronger result to prove that its square is multiple 4, is divisible by 4, but that's not what they ask us to prove. And so you only need to factor out the 2 here in order to show it's even. All right. We also talked about the definition of an odd number. Okay, so how do we describe an odd number? Katie? How would you describe an odd number? Symbolically like this.
Is it 2 times k plus 1?
Yes, 2 times k plus 1, and also this k is an integer. All right, because any odd number can be obtained by adding 1 to an even number. So that's how we define it. And you could also do 2k minus 1 if you want, 2 times k minus 1, because any odd number can also be obtained by taking an even number minus 1. So that 2k part right there, it's an even number. Either add 1 to it or subtract 1 from it. Either way, you're going to get an odd number. But normally, we like the first form because it's plus. Plus is usually easier than minus. But if you want to do 2k minus 1, that's also correct. Okay, so that's the definition. So like I said, when you do the problems in this section, assume that's the only thing you know. And the definition, an even number is 2 times the integer. Odd number is 2 times the integer plus or minus 1. We are going to look at, so we did a proof question. Another type of question is If it's incorrect, you give a counterexample. So we did do that in last week's homework. In your homework this week, under 3.1, determine whether the statements is true or false. Justify your answer with a proof or a counterexample. So the questions here, last week I told you if it's true, you don't need to provide any proofs because we haven't learned any proof yet. And so, but this week you do. So there are three statements given here. For the first one, the negative of any odd integer is odd. If you think it's true, so first you got to determine whether it's true or false. If you believe it is true, you got to provide a proof. If you think it's false, give a counterexample. So you got to justify your answer. Similarly for the other 42 and 45. I think we can do one or two more examples. If I want to prove the product of any two odd integers is odd, Oh, yes, please, thank you. The product of any two odd integers is odd. Can you see well with this marker? Yes, okay. All right, so what are we given? What did we start with? What do we know?
Multiplying two odd integers?
Yes. We are given two odd integers. Well, we start with two odd integers. And we need to show the product, which means you multiply these two odd integers is odd. So it's more like this. So we start with what's given. We're given two odd integers. And you're going to try to fill in the blank. And to prove the product of these two is even. So the product is even. Product, of course, these two integers. So let's start with two odd integers. Can I pick 3 and 7? Can we do that?
Yes.
Sure. Yes? Yes?
Yes.
No, we can't. Okay.
No.
No, you can't. So when you pick 3, and if you do that, say I'm going to pick 3 and 7, 3 times 7 is 21, that's odd. This will just be considered as an example. It's not a proof. So this is not a proof. Why? Because in the problem it says very clearly, you got to show the product of any two odd integers. Did they tell us which two odd integers they are? No. Unless I change the question, say, prove the product of 3 and 7 is odd. You will use 3 and 7 given. But if they didn't tell you these two odd integers are 3 and 7, you cannot assume they are 3 and 7. In fact, you need to prove any two odd integer. So there would be, how many odd integers do we have? Infinitely many. So theoretically, you're supposed to prove. If you want to do this way, you're going to have infinite many of them. You got to do 3 times 7, 3 times 9, 3 times 1, 3 times 11, 3 times any. You got to check all the odd integers, all the pairs of odd integers, even including negative odd integers. So you have to check negative 7 times 3, or negative 1 times 3, negative 1 times negative 7. And if you try to do this way, it's impossible because there's no way you could list all the pairs of odd integers and to show it's even. Yes, if you do a few of them, that's correct. That's even. But unfortunately, you cannot do this way anymore. Okay? Because this way, if you want to do this way, you have to list all the infinite many cases, which we can't list infinite many cases. So let's not pick special numbers anymore. when you pick them, how do we represent any two odd integers? Yes. So when you can pick, you will have to use the algebra, the symbolic form. But when you use 2k plus 1, then because this k is a variable, so let's let 2k plus 1 be one of the odd integers. But because we have two of them, you got to pick another form. 2 times the integer plus 1. Can I still use 2k plus 1? Can I say 2k plus 1 and 2k plus 1? No. Because did they tell us these two odd integers are equal? No. So you're going to pick a different letter to represent that integer. You can pick a 2l plus 1 be two odd integers. Where k and l are both integers. K and l are both integers. So let's look at this again. So why do I have to use 2k plus 1, 2l plus 1? Why cannot we pick specific numbers like 3 and 7 or 3 and 11 or 5 and 20? Yes?
Could you use 2k plus 1 and 2l minus 1?
Yes, you can. Yes. If you want, yes, you can. So first of all, you cannot use specific numbers. And because if you do that, you only prove the one case. You proved, suppose you show me, if you wrote down a few cases, 3 times 7 is 21, it's odd. Negative 1 times 3, negative 3, that's odd. Negative 1 times negative 7 equals positive 7, that's odd. If you give me this, it's not a proof of the problem because you only proved the 3 cases. So, okay, for these 3 pairs of odd integers, yes, that is right. But you didn't prove any 2. So there. What about 5 times 9? Well, you didn't show me. And what about 11 times 13? And you didn't show me. So that's why this will not be considered as a proof. It's just some special cases. Okay, so but that's why we cannot pick numbers. We have to pick those variables. Secondly, why can we use 2k plus 1, 2l minus plus 1? Because that's the definition of odd integer. Because they told us we have 2 odd integers. And the definition of odd integer, it's an even integer plus 1 or even integer minus 1. Like I said, James just asked, for the second one, can I use 2l minus 1? Yes, you can. Or can I use 2k minus 1? Yes, you can. In general, we prefer plus because addition is easier than minus. And the other thing is 2k plus 1, 2k minus 1. So the definition of odd integer is 2 times an integer plus 1. But we don't like to use a word in there. So you got to pick a variable, a letter for that word integer. So normally you pick k, l, m. If you say you want to use x, y, z, you can. But usually we like to use save x, y, z for variables. So we use k, l to represent those letters to represent like a constant. So it's some kind of integer, but we just don't know what that kind of integer is. Okay, so that's the first thing. And the other thing is you got to pick 2 different letters because that integer may be different. So they may not be the same integer, same odd integer. Okay, so we have 2 odd integers. Now next we try to show the product of these 2. So we're going to take the product of these 2, which is 2k plus 1 times 2l plus 1. That's the product. When you look at them, can we tell whether it's odd or even? We can, right? So again, how do you show a number is odd? You must show it has this format. What format? 2 times the integer plus 1 or 2 times the integer minus 1. It has to have this format. When you look at this, it doesn't have that format yet. It has a multiplication here. So we're going to go ahead and use algebra to multiply this out. You can do FOIL. We get 2k times 2k, which is 4kl. Okay, and let me move it to the next page. Equals 4kl, and 2k plus times 1, you get 2k. And 1 times 2l, you get 2l. And 1 times 1, you get plus 1. So that's just from algebra. Okay, now we got this, after we multiply out, we got this expression. And remember, we want to show this is odd. And when you look at, so far, we don't have that formatted yet. Because the format, the definition we need is always this. Keep this in mind. Whenever we have odd, it's 2 times integer plus 1. So I try to match this format. Look, it's getting close. There's a plus 1 plus. It's very close now. So that plus 1, you're going to leave it there because you want, so the format we want is 2 times some integer right here plus 1. So that's why I know I should save the plus 1 there and keep that plus 1 there. And next, I need to have a 2 times something. So for the rest of these terms, we can try to see if we can factor out the 2. And look at that, by algebra, we know that they have a common factor 2. So let's factor that out. Okay. Can everybody see what I did over here? Yes. Okay. And why did I do this way? Why did I leave a 1 out? And because I want to match the definition, 2 times the integer plus 1. So right now, when you look at this, that's exactly what we need. You don't have to mark this, but I'm going to try to put it here to help you understand why we did this. Why did we factor out the 2? Because we wanted to match the definition with odd number 2 times the integer plus 1. Okay, so now you can say, you can add one more sentence, say, since K and L are both integers, 2KL plus K plus L is integer. So that part right there, whatever in the parentheses, it's K is integer, L is integer. So when you multiply 2 times the integer and the integer, plus the integer, plus the integer, you're still going to end up with the integer. You're not going to get a fraction here. So that whole thing right there in the parentheses is integer. That's exactly what we need, 2 times integer plus 1. So we can say that is odd. 2 times 2KL plus K plus L plus 1 is odd. Okay. Maybe we should go ahead and add that in front, the original what we started with, 2K plus 1 times 2L plus 1. Because how did we get this? We got this from factoring the 2 out, and that expression is obtained by multiplying these 2, right? So if you want, you can go ahead and write down 2K plus 1 times 2L plus 1 equals this form. So that tells us if this is odd, of course, that is odd. And that's the product of 2 odd integers. So maybe it will save you one sentence. Instead of saying, okay, and the 2K plus 1 times 2L plus 1 is odd, so you can put them together in one sentence. Any question about this example? Okay. So the homework question, some of them they ask you to do the product or the difference, and you just do whatever operation they tell you to do. Now, a counterexample case, it will be like the one we did before. So if I say the sum of 2 odd integers is odd. If I give you, let's say, example 3, the sum of 2 odd integers is odd. First, determine whether this is true or false. Is this true?
No.
No, it's false, right? So the statements, if they didn't tell you whether it's true or false, you can pick some numbers to check whether it's true or false. So I can, in this case, this one is false. How do you prove a false? You provide a counterexample. That's when you can pick special numbers. 5 plus 7, I got 12, which is even. I didn't get an odd integer, not odd. So this where I picked an odd integer 5 plus an odd integer, I actually got a not odd. I got an even number. So this will be a counterexample. So when you prove something is false, it's very easy. You can pick special numbers. But if you want to prove a statement is true, you cannot pick special numbers. You will have to use the variables. Any question about this section? No? Okay. Later we will have more complicated problems to do to prove whether a number is even or odd, or even like questions multiple, prove something is a multiple of 3 or multiple of 4. The idea is very similar to this. Now let's look at 3.2. So we talked about odd and even. Now we're going to talk about rational numbers. So we're still going to talk about direct proof, but this time we are going to look at rational numbers. So direct proof part 2, rational numbers. And we mentioned the rational numbers before. What kind of numbers are rational numbers? Give me, if you don't remember the definition, what is the example? Give me an example. Huh? Megan, can you give me an example of a rational number?
5.
5 is rational? Yes. Any other examples? Do you have something different?
Any number that's not a fraction?
Oh,
Or no, any number? Oh,
any number that's
Actually-
not a fraction that's repeated.
Any number that is a fraction. Okay, get rid of not. So rational number, it's including 2/3. But 5 is also rational because 5, you can write it as 5/1. That would still be considered as a fraction. It's just not a simplified fraction. So rational number is the same as fraction. Okay, easy way to put that. So there is a formal definition for a real number. So what is a real number? A real number is not definition of real number. I'm talking about a real number is rational if you can write it if and only if. Notice in our definition they always use if and only if. It can be expressed. It can be expressed as a quotient of 2 integers, which means fraction. A quotient of 2 integers with a non-zero denominator. Of course, for fractions, the bottom number, the denominator cannot be 0. With a non-zero denominator. Okay. So on Monday, I mentioned that in this chapter, we're going to learn 3 different types of proofs. One is called direct proof. And then we're going to learn indirect proof. And when we talk about indirect proof, we're going to try to prove a number is irrational. So that's the definition of rational. What would be the definition of irrational? What's the definition of irrational? Well, simply put, if it's not rational, right? So irrational means not rational. Now explain a little bit more. What do we mean by not rational? Rational means it can be written as a fraction. A fraction is integer divided by integer. So the rational, what's a rational number? You can always write it as integer divided by an integer. That's the quotient. Pretty much a fraction. But also notice the bottom cannot be 0. So that's an integer, a rational number. So when you have an irrational number, it means you cannot write that number as a fraction. Make sense? Okay. So if you took Math 3000, History of Mathematics, in that class, I did ask, one of the homework questions is to prove square root 2 or square root 3 is irrational. So, for example, square root 3 is irrational. How do you prove that? If you want to prove that, you're going to have to show square root 3. You cannot write square root 3 as, there's no way you could write square root 3 as any integer over integer, which means a fraction. You cannot do that. And it is hard to do, to prove anything is irrational because, again, there are infinite many fractions. So if you want to show square root 3 is not a fraction, theoretically, you're supposed to check every single fraction we have. to see they don't match. Any single fraction, its value is not the same as square root of 3, and which is impossible to do, right? So for that kind of question, irrational is very hard to do. But later we will talk about, when we talk about indirect proof, we won't prove it directly. The direct way will have to be checking every single fraction to see it's not equal to square root of 3. But it's impossible. So later we're going to talk about indirect proof. So in this section, they will not ask you to prove anything is irrational because that's impossible to do. So all the questions will be asking you to prove why this is rational. Okay, so how do you prove something is rational? Just like what we discussed, how do you prove something is even? How do you prove a number is even? You have to show whatever this number is can be written as what? What format? 2 times the integer, right? Okay. The integer usually is a algebraic expression with a variable in there. And similarly, if you want to prove something, a number is irrational, you have to show this. You can write this number as an integer divided by an integer. Simply put, a fraction. So if you want to just say a fraction, an easy way to help you remember this. Irrational means fraction. Fraction is rational. And again, we don't like to use words. So usually we pick variables for the integers. So you can pick a variable for the top integer and a variable for the bottom integer, anything you want. We're going to follow textbook. You can pick A over B, C over D, anything. So I'm going to use A over B. A to represent the top integer, B to represent the bottom integer, and this B is not equal to 0. B is not equal to 0. Okay. All right. So if they tell us a number is rational, you immediately replace it with this algebraic form, A over B. If they want you to prove a number is rational, you're going to have to show the top is integer and the bottom is integer. Okay. So let's start with the example. Well, the homework you will still have 2 types of question. First, they gave you a statement. You got to determine whether it's true or false. If it is false, you give a counterexample. If it's true, you prove it. Okay, so I'm going to. The homework is product and the difference. So I am going to do the quotient and the sum. All right, so let's look at example 1. I'm going to start with maybe the sum of any 2 rational numbers. Rational numbers is a rational number. Now, what's given? Or, in other words, what should we start with?
We want rational number.
Yes, 2 rational numbers. That's right. So we're given this. That's given. Because we want to show the sum is rational. That's what you need to do. The goal. And what's given 2 rational numbers. So when we start, we say, okay, so we got 2 rational numbers. And don't pick 2 special fractions, like 1 over 2 and 3 over 4, to add them to see whether you get a fraction. So we're going to have to pick, because these 2 rational numbers, or you can say, in other words, 2 fractions. We don't really know what kind of fractions they are, but we're going to have to use the variables. Let A over B to represent one of the fractions, because there are 2 of them. So let's pick a different one, C over D. B 2 rational numbers. Rational numbers. Where specify A, B, C, D, they are integers. A, B, C, D are integers. And B is not a 0, and D is not 0. So the reason, first of all, it comes from a definition. What's the definition of rational number? It's the quotient of 2 integers. So there's a top integer A, bottom integer B. Similarly, top integer C, bottom integer D. And that's why you're going to specify A, B, C, D, they are integers. Because it's possible, if you only have a quotient, let's say if I give you something like this. square root 3 over square root 2. Is this a rational number? No. When you have square root 3 or square root 2, or even one of them is square root, these are all irrational numbers. They're not rational, although you can put it in the form of a quotient. See, something divided by something, something divided by something. But these are not considered as rational numbers because in the definition, although they look like fractions, and they are not rational numbers because the definition, the top has, both of them have to be integers. Square root 3 is not an integer. Square root 2 is not an integer. Although in the second example, 2 is an integer, but square root 3 is not. So you got to make sure both are integers. So that's why we have to specify that. Okay, so we got two rational numbers. The reason you have to pick different letters because they didn't say these two rational numbers are equal. So you're going to have to pick different letters. And notice A and B, they can represent any integer. So this form, A over B, can represent a 1/2, 3/4, 7/11, or 12 over 14. So they can represent any rational numbers you can possibly have. So they will represent implemented fractions. So now we're going to do addition. The sum, we do addition. A over B plus C over D. Now by looking at them, can we say, well, this is rational? You can't, not yet, because if you want to say anything that is rational, go back to look at the definition. It has to be an integer on the top divided by an integer on the bottom. That's a quotient of integer divided by integer. So when you have this format, there's a plus sign there. That is not the format we need. So the final format should look like this. A single integer on the top, an integer on the bottom. So right now, it's not that form yet. So we're going to do algebra by adding them. How do we add two fractions? Find the least common denominator, which is BD. Can everybody see that? Okay. So that's something from the algebra class. If you forgot how to do that, maybe send me an email. Let me know. I can make some videos and post on Blackboard. So the least common denominator is B and D. So you're going to try to equal the denominator. The first fraction, we multiply both the top and the bottom by D. Second fraction, we multiply both the top and the bottom by B. You're going to get a common denominator, which is BD. Now we add the numerators. AD plus BC. Well, really, I don't need that next part. So look at this answer here. Does it have the format we need for a rational number? Integer on the top divided by integer on the bottom. Look, this is a quotient, and on the top, it's AD plus BC. Is that an integer? AD plus BC? Yes, because A, B, C, D are all integers. So A is integer times D are integer, you still get integer, plus B times C are integer. So the top, apparently, it's an integer. And the bottom, BD, also, it's an integer. And also, the bottom will not be equal to 0. BD is not 0. How do we know that? That's right. B and D are both not 0. So B is not a 0 and D is not a 0. So when you multiply two non-zero numbers, it's not going to get 0. So this fraction, this rational number is defined, well-defined. You won't get like undefined situation. Okay, so we finished the... when we get here, you can pretty much say, you get this. We can add one more sentence just to explain a little more. Since AD plus BC is an integer, and B times D is also integer, and BD is not equal to 0. You can say A over B plus C over D equals AD plus BC over BD is rational. And why can we say it's rational? Because it's the definition of rational. Integer on the top divided by integer on the bottom. A non-zero integer on the bottom. That has to be a rational number. Okay. All right. So you do have to add them to get a quotient, a single quotient, not just by looking at AB over plus CD. Although it's like a common sense. From algebra class, we know whenever you add two fractions, you're still going to get a fraction. But you cannot assume that. You have to show it is an integer divided by integer. Well, example 2. I'm going to do another quotient. So example 2, the quotient of 2 in this case, I can the quotient of 2 there's a little bit problem here. The quotient of 2 rational numbers, I gotta make sure I have to say something that the second quotient. The second rational number is non-zero because you cannot divide a number by 0. So I probably should specify the divisor. The divisor is non-zero. Otherwise, we cannot divide them. It will be undefined. Is rational. Okay, so in this case, we're still given 2 rational numbers, but notice the second rational number is non-zero. So we're going to say let A over B and C over D be 2 rational numbers. And where A, B, C, D are integers. A, B, C, D are integers. B is not 0, C is not 0, and D is not 0. Notice that I added one thing. I added that C is not 0. Why did we? Previously, in the first example, we didn't have that. So in the previous example, we just need to say the bottom numbers are non-zero. If top is 0, that's okay. For example, you could have 0 divided by 5, which is just the number 0. That's fine. 0 is still considered rational, as long as you can write it as integer divided by integer. So 0 is still rational. So I don't have to make sure the top is non-zero. But in this case, I do have to say this one is non-zero. Why?
Because you're dividing the 2 fractions?
Yes. Think about it. If this C is 0, what's going to happen? If C is 0, 0 divided by a non-zero number, you're going to get 0, right? So then you will have to take A over B divided by 0. And we know, let's give you example, 5 over 3 divided by 0. Can we do this? No, it's undefined. We know you cannot divide anything by 0. So that's why I got to make sure C is not a 0. It's a non-zero divided by non-zero, you get non-zero. For addition, that's fine. You can add a 0 to anything. It's defined. But division, you cannot divide any number by 0. Okay, so now we're going to do the quotient. Divide A over B by C over D. A over B divided by C over D. How do we divide 2 fractions? From algebra class? Yes, keep the first fraction, you change the division sign to multiplication, and you flip the second fraction. And how do you multiply 2 fractions? Multiply straight across. Okay, so you don't have to equal denominator like the addition we did. It's much easier. You do A times D on the top, B times C on the bottom. Okay, take a look at the final answer. Does this have the form we want for the definition of rational number? So think you gotta memorize the definition of rational number. It's an integer on the top, divided by an integer on the bottom. Is this an integer? Yes. Is that a non-zero integer?
Yes.
Yes. Do you know why the bottom is non-zero?
Because we stated it.
B is non-zero, and if you look at the beginning, B is not a 0, C is not a 0. So when you multiply 2 non-zero numbers, you still get a non-zero. So you're going to say something like this. Since AD is an integer, BC is also integer. So you get integer divided by integer. and also BC is not equal to 0. We have A over B divided by C over D equals AD over BC is rational. Okay. Well, any question about these two examples? All right. So you should be able to follow these two examples to do the homework. I'm going to give you one more. Let's say the sum of two irrational numbers is irrational. Okay. Previously, we did the first example we did. The sum of any two rational numbers is still rational. We proved it. We proved it. Rational plus rational, we still get rational. But what if I say this statement? The sum of two irrational is still irrational. Would this be true? Yes or no? If you say yes, then you have to prove it. If you say no, you give a counterexample. And this one is false. Why is it false? If you say it's false, you only need to give me one counterexample. You can pick specific numbers. Which two rational numbers, after you add them, you could get you don't get a rational. So we are given two rational numbers. They're saying when after you add them, sum, you do addition. After you add them, you're gonna still get an irrational number. But we say it's false, which means the counterexample you're gonna give me, you add an irrational number and another irrational number, you actually get a rational number. So can you come up with an example like that?
The square root of 4 plus the square root of 16.
Square root of 4 will not be, although it looks like irrational, but square root of 4 you can simplify it to a 2, which is 2 over 1. That would be considered as rational. Okay? So you cannot give an example of square root of 4 or square root of 16 because square root of 16 can be simplified as 4, which is also rational. Okay? So you have to give two irrational numbers. But you can give square root of 3 plus what?
Square root of 7.
Negative square root of 3. Square root of 3 is irrational. Negative square root of 3 is also irrational. When you add them, what do you get? 0, which is rational. So that's a counterexample. Okay. Okay, questions? All right, so one important thing is that you need to get used to is if you say something is false, you just need to find one example. We talked about this before in chapter 2, chapter 1, also chapter 2. So when I say, if I make a claim, say all school buses are yellow, in order to prove I am wrong, all you have to do is to find one school bus that is not yellow, right? You don't have to find every single school bus on the whole world and show me the bunch of non-yellow ones. You just need to find one, then you can prove that I am wrong. But if you say, I want to prove all the school buses are yellow, I want to prove you that it's true, then I have to find every single school bus in the whole world and show you every single one is yellow, okay? Which is pretty much impossible to do because there are probably lots of them, right? So, okay, so the same way, if you want to prove it's false, you can give me one counterexample. If you want to give me more, that's fine, but one is sufficient, one is enough. But if you want to prove something is true, you won't be able to just pick two fractions, two rationals, and add them to show me, well, 1/2 plus 3/4 equals 5/4. That's still rational. That's not example. That is an example, but not a proof. So when you do the proof, you cannot measure ones. You got to pick use the variables. They can represent any two rationals. All right, so that's chapter 2. Now, chapter 3. Chapter 1 and chapter 2, I think they're very easy. Chapter 3, It's going to be a little harder, but if you memorize the definition, it's not going to be too bad. 3.4. And this is something, 3.3. This is something in number theory. That's one of the main things you talk about in number theory class. So you probably will go back to this in that class. So we're still continuing direct proof, part 3. This time we talk about something called divisibility. Divisibility, we mentioned it before. Let's say 6 is, some examples, 6 is divisible by 2. So for example, we say 6 is divisible by 2. Any other ways to describe this? 6 is divisible by 2. Wait, 6 has a factor 2. Any other way? 6 what? 6 is even? Oh, well, yeah, in this case, it's because it's 2, right? Yes, but in other cases, you won't be, like if I say 6 is divisible by 3, then you won't be able to say it's even, right? So, yeah, that's a special case. You can say that for this, but that's not general for other cases. But any other way besides these two? Besides saying 6 is divisible by 2 or 6 has a factor 2, any other ways? You can also say 6 is a multiple of 2, right? Okay. Any other ways? We actually have many ways to say this. You can also say it backwards. You can say 6, if I reverse change them, you can say 6 2 divides 6, right? 2 divides 6. You can add a word evenly, but you don't have to. Usually when we say divide 6, it means divides evenly. You can also say 6 is a factor of, I keep saying 6. 2 is a factor of 6. But it's kind of the same as 6 has a factor 2. But we can also say that. Or the word factor, there's another way to say that. You can also call it a divisor. It's the same thing, divisor. So there are so many different ways to call this, to say this. A lot of times, so the way we're going to talk about mainly is going to be using the first one and this one, I guess these three. So when we define it, we're going to use the 2 divides 6. So we're going to define that, or the first one. So we're going to create a symbol for that. 2 divides 6 or 6 divisible by 2. So these two are the same thing. But in the definition, we kind of like following 6 is multiple 2. So let's write down the definition. So what do we mean by saying 6 is divisible by 2? Why did you say 6 is divisible by 2? What does that mean? It means what? 6, you can write 6 as 2 times a integer 3. Well, why cannot we say 5 is divisible by 2? Because you cannot write 5 as 2 times a integer. There's no such integer that you can do that. We know actually you should have a fraction here, 5 halves, right? So that you're not going to get an integer. So that definition, although everybody knows, well, I just know 6 is divisible by 2. Yes, that is true. But we want to define it formally. Whenever we say 6 is divisible by 2, or 2 divides 6, or sometimes we say 2 goes into 6. What does that mean? We mean you can write 6 as 2 times the integer. The reason for 2 not going into 5 or divides 5 because you cannot write 5 as 2 times any integer. So let's write down the definition. In general, if we have the text, we use the N and the D But in general, we could use A and B. Well, I'm going to follow the textbook here. So when we define n is divisible by d, n is divisible by d. Or in other words, we say d divides n. The other way to say it, d divides n. We're going to define it as if and only if. So I'm going to use this symbol from now on to represent if and only if. So it means we know when you do this from previous class, we know when we talk about conditional statement, we draw this to represent implication, and you could have both directions. When you have both of them, you could mark them like that. So which means if n is divisible by 6, there exists integer k such that n equals d times k, or k times d. Okay. All right, so let's take a look at this one more time. You do have to memorize this definition. In 3070, in number theory class, you're going to use this definition again to do whenever you do proof problems. By the way, we also have a symbol for this. D divides n. You write down D, you draw a vertical line, and you put n there. D divides n, or n is divisible by D. By the way, this symbol, don't confuse this symbol with the slash we have. Let's say the example, 6 is divisible by 2. Or we say 2 divides 6. When we use the symbol to describe it, it's 2 divides 6. Don't use the slash. Because in the past, I had a student thought it's like 2 over 6. 2 over 6 means 2 over 6, or 2 divided by 6. It's not the same as 2 divides 6. 2 divides 6 actually means 6 divided by 2 is equal to 3. So this, in fact, means 6 divided by 2, you will get integer 3. So be careful, they are not the same thing. It's different from the symbol we had before, the slash. Okay, this is a vertical line straight down, not a slash. So like I said, in fact, 2 divides 6 means you do it backwards. 6 divided by 2, not 2 divided by 6. When you divide 6 by 2, you will get an integer 3. So let's look at the definition one more time here, how to memorize this definition. But if I want to prove 6 is divisible by 2, D here means divisor. D is divisor, so D goes into n. When we prove it, I need to show this number 6. The 6 can be written as the divisor 2. This is divisor 2. That's the integer n. I need to write in 6 as a divisor 2 times the integer 3. If I can find this integer 3, then it's divisible. If I cannot find an integer to get that, and it's indivisible, it's not divisible. And when you look at, let me write this down here separately so you can see better. So 6 is divisible by 2. How do we prove it? Or you can say 2 divides 6. Divides 6. And how do you prove it? You would use the definition. The definition says, so this is our n, this is our divisor 2. We're going to have to find an integer k such that n equals d times the integer k. So in this case, that would be, I need to find the integer k, this k is a question mark here, such that 6 equals divisor 2 times some kind of integer. So does this integer exist? Can I find an integer such that 2 times that integer equals 6? Yes, which is 3 in this case. If that integer exists, okay, yes, 6 is divisible by 2. So when you memorize the definition, it's better to use the other form we discussed, the other sentence, this third one here, 6 is a multiple of 2. It's the same thing. 6 divisible by 2 is the same as 6, saying 6 is a multiple of 2. So because when you look at the definition, so this is a definition, and if you take a look at it, that says very clearly 6 is a multiple of 2. A multiple, if the multiplier you use is 3, multiple multiplication of 3. So when you memorize the definition, it's better to use this way. Say 6 is a multiple of 2. Now, with that, with the definition, we can try to do some proof problems. So let's start with an easy one. Let's say, how do we prove 3? Well, we know how to prove 2 divides 6. You just write down 6 as 2 divided by 3. Oh, by the way, I did see in the past some students did a different way. So they probably learned from other classes. And so some other instructors may show you this way, say 6 divided by 2. How do you prove 6 is divisible by 2? So I take 6 divided by 2. I got 3, which is an integer. You can do this way. But I'm going to prefer the way we do in, I'm going to follow the textbook. That's the common way we usually do in number theory. But this also is correct. When you take a look at these two, they're the same thing. Can you tell? So the difference is you divide both sides by 2. If you divide both sides by 2, this 2 cancels that 2. You got 6 divided by 2 equals 3, right? You get the fractional form or division form instead of multiplication form. Sometimes, adding fractions is not that easy to do, so it's probably better to do this way, but sometimes maybe it's not, for those students, if you don't think fractions are too bad, you can use the other form. So when I do the multiplication way, 6 equals 2 times 3, I just need to show this 3, it exists. Or you could do 6 divided by 3. I do get an integer. Yes, the integer exists. So that's the other way to do that. But again, I'm going to stick to this way, the definition, formal definition. So the example, first one we're going to do is to prove 3a plus 3b is divisible by 3. Where a and b are both integers. Where a, b are integers. That's what we need to prove. 3a plus 3b is divisible by 3. So what expression do we need to show? By the definition. Follow the definition here. So I'm going to show you the definition one more time here so you can refer to that. In order to show n is divisible by d, you have to show n equals d times a integer. Okay, so that's the definition. So I want to show 3a plus 3b is divisible by 3. That means I need to show what? 3a plus 3b equals, yes, 3 times a integer. Can we write 3a plus 3b as 3 times an integer? Yes. You just need to factor out the 3, right? And a plus b is an integer because they told us a, b are integers. So since a, b are integers, a plus b is also an integer. And from that expression, it tells us 3a plus 3b equals 3 times a plus b is divisible by 3. So in the other words, from this example, you can see, how do you prove something is divisible by 3? If you can factor out of 3. Factor out 3. If you want to show something is divisible by 2, you factor out of 2. If you want to show something is divisible by 4, you need to factor out of 4. So that's what you need to do. Okay, I guess one more example, also easy one. Prove 10 km is divisible by 5. Again, km are integers. So we show this is divisible by 5, which means by the definition you need to show, okay, this time I'm going to just write down since 10 km equals. So that means, like what I just summarized before, if you want to show something is divisible by 3, you factor out of 3. If you want to show something is divisible by 5, you need to show that you are able to factor out of 5. Can we factor out of 5 from here? Yes. 5 times 2 km. Okay, and that is exactly the definition. This number equals 5 times the integer, and that part is definitely an integer. And the 2 km is an integer. We say, I'm going to use the short form instead of sentences. I'm just going to use the notation we have, 5 divides 10 km.
Can you move your page up just a little?
Yes. All right.
Thank you.
All right. Any question so far? Okay. Now, next we are going to, let's see, I'm going to prove one oath. So we want to prove for all integers a and b. So this is an example in the textbook. Example 3.3.8, which is on page 150. In the third edition, if you have other editions, just try to find I think it's probably your chapter 4. Try to find the divisibility section. So it says prove that for all integers, I'm going to use the symbols instead of English words. So remember we talked about this? This means for all. To replace the words, for all integers a, b, and c, if a divides b and b divides c, then a divides c. So in this case, we don't have any numbers. We just have all variables. Okay, so how do we prove this? What's given?
A, B,
Well,
and
when
C
you-
are integers.
Yes, A, B, C are integers. What else? What do we start with? What do we know?
A divides B.
And
B divides C.
yes, that is given. Both are given. We're given both. Well, it's very easy to determine what is conclusion. What do they want us to prove? They want us to prove A divides C, right? So if you found what they asked you to prove, pretty much what's the rest of them should be given. So when we are A divides C, it's only when both are true. When A divides B and B divides C, then you can get a conclusion A divides C. So these two are conditions, hypothesis. So that's considered as given. Okay. All right. So when you do that proof, and when you think about it, if you plug in numbers, that would be true. Say 2 divides 6 and 6 divides 12. Can you get a conclusion? The first number, A divides 12? 2 divides 6. It's like 2 goes into 6. 6 goes into 12. Can we say for sure the first number 2 goes into the last number 12? Yes, right? It seems like it's always true. But this cannot be used as a proof. So this is not a proof. This is just an example to confirm this is true. You have to show it's for all the numbers. Just like when I say all school buses yellow, I cannot just pull out like one school bus, one yellow school bus, say, look, this school bus is yellow. then I'll tell you all other school bus is yellow. That's not true, right? So you cannot just use one case, one example to show all of them are true. So the same way here, I cannot use this as proof because this is just like one yellow school bus. I have to show it's true for all integers. So don't pick special numbers. So all you have is the definition. But if they tell us A divides B, what is the definition of A divides B? If A divides B, what does that mean? What's the definition? There exists an integer k such that what?
N equals E times K.
It should be the other way around. Excuse me. A divides B. When we read it, it's also B is divisible by A. So be careful with the symbol. So when we put 2 divides 6, it means 6 is a multiple of 2, or 6 is divisible by 2. So when you write it, usually the number on the right is bigger. So you got to put the number on the right first. B equals A times K. Similarly, they also told us in the condition B divides C. What does that mean by the definition?
There exists an integer k.
This time we're going to use a different integer, L,
Okay.
such that which one equals which one?
C equals B times L.
Yes. The reason we have to use a different letter is because, okay, this K and L here, it means A goes into B how many times, right? So, for example, when I have 2 divides 6, means I can write 6 as 2 times 3. What does this 3 mean? It tells us 2 goes into 6 3 times, correct? Okay, so the same thing here. This tells us A goes into B k times, and B may not go into C the same number of times. So that's why you have to use a different letter. Okay, so now, how do I show A divides C? This is a question. This is my thinking part. So in order to show A divides C, I need to go by the definition. When can we get A divides C? When can we say A goes into C? Definition will be what? You can find an integer such that which one? C equals A times A integer, right? So if you can write C as A times integer, which means A goes into C this many times. So the question is, how do I know if this integer exists? So that's what we need. C equals A times something. How do we get C equals A times something from these two equations we already have? Yes, very good. Substitution. So you can substitute in the second equation, C, you can substitute that B for, substitute A times K for that B. Replace this B with A times K. Okay, so B is AK, so I'm going to replace that B with AK. So you got a C equals AK times L. And I can put K and L together. And look, that's exactly what we need. C equals A times A integer. It tells me A goes into C KL times, this many times. Okay, or that's just the definition. If you can write C as A times the integer, then A goes into C, or A divides C. So A divides C. Well, if you want to explain, because KL is integer, so maybe it should add one more. Since KL is integer. Okay. Well, I guess I'll give you more examples next week. And that's all for today.
Your meeting has ended.